If you can't trace it, you can't fix it. This shows the exact span that's killing your P95. By the end, you will understand how to add tracing to an LLM pipeline, so you can point to the single span that drives tail latency. I'm Professor Pi, teaching AI engineering and LLM systems with simple Python. Real systems mix retrieval, tool calls, and model generations. That mixing is where latency hides. A request can spend most of its time waiting on one small step. Tracing lets you see each step as a span. And then you can compare durations and P95 behavior across requests. Success means you can answer whether slow requests come from retrieval, a remote tool, or the model itself. At the core, tracing is just timed labels glued to code. A root span represents the whole request. Child spans represent substeps. With those spans, you can calculate per span P95 and find the worst offender. Tracing is lightweight and works across services when you export traces to a backend like Jaeger. We will build a tiny traced pipeline that shows retrieval, a tool call, and generation. You will see how a tracer is created, how an exporter sends traces to Jaeger, how child spans are made, how sampling controls overhead, and how to compute P95 latency for the whole operation. Now let us jump into the first piece. This snippet initializes an OpenTelemetry tracer and emits a root span. It shows creating the tracer resource and starting a root span that represents a single LLM request. The key idea is to name the root span after the high-level operation, so every child span nests under it. You will see lines that set service attributes on the tracer resource, and a line that starts and ends the root span around the whole pipeline. The root span captures total time and propagates context. If you change the service name, you alter how traces group in Jaeger. And if you omit the root span, you lose a single view of request total. Now, we will connect the tracer to a backend for storage and viewing. This example wires the OpenTelemetry OTLP exporter to Jaeger for trace export. It configures the exporter endpoint and registers a span processor that batches and sends spans out. The essential bits set the OTLP exporter target and attach it to the tracer provider so spans flow to Jaeger. You will also see optional resource attributes that tag traces with a service name and environment. Increasing batch size or send interval improves throughput but raises memory use. With this exporter in place, you get searchable traces, flame graphs, and timing per span in Jaeger, which turns local timing into actionable data across services. Next, we will carve the request into logical substeps. This code creates child spans for retrieval, tool call, and generation. It shows starting a child span for retrieval, recording its duration, then starting a child for a tool invocation, and finally a child for the model generation step. The top-down flow mirrors the real pipeline. Retrieval runs first, then a tool is called, then the model generates. Inside each child span, you will see simulated timings, or actual I/O calls, and attributes like document ID or model name. Those attributes make the traces searchable, so you can filter by document or tool. If you widen what each span covers, you get coarser timing. If you split more finely, you gain detail but add overhead. Now we will control how many traces we keep. This example sets a parent-based TraceIdRatioBased sampler in OpenTelemetry. It configures a sampling ratio so only a fraction of root traces are kept, while honoring parent sampling decisions for child spans. The paragraph configures the sampler with a numeric ratio that controls how often full traces are recorded and exported. A lower ratio reduces load and cost but makes rare slow events harder to observe. A higher ratio gives better visibility into tail latency at the expense of exporter bandwidth. This setup is ideal for production where you want representative sampling, but need the option to raise sampling when debugging. Finally, we will run the pipeline and compute an aggregate. This snippet runs a traced pipeline and reports its P95 total latency in MS. It repeatedly invokes the traced request, collects the route span durations, and computes the 95th percentile across runs. The important idea is aggregating durations from the route span so you measure end-to-end P95 for the pipeline rather than a single run. You will see code that records durations into a list and then sorts to pick the P95 value, expressed in milliseconds. Changing the number of runs affects statistical stability. More runs make P95 estimates steadier, but cost more time to measure. In a real project, you would map those toy timings to production log streams and export sampled traces while keeping metrics for every request. The pattern stays the same. Instrument route, add child spans for each component, export sampled traces, then compute P95 from route durations. Recap. What it is: distributed tracing for LLM systems that breaks a request into a route span and child spans so you can see where time is spent. When to use it: when you need to find the source of tail latency across retrieval, tools, and model generation. One caveat: tracing adds overhead and export costs, so use sampling and targeted attributes. Wrap punch. The next step is to tune the TraceIdRatioBased sampler value to balance visibility and costs, and then raise sampling only for problematic endpoints to capture more traces for analysis. If short, practical AI engineering helps, subscribe and watch the AI engineering videos.